The interlacing of dimensions at the quantum level, a comprehensive exploration. The concept of dimensions has long fascinated scientists, philosophers, and mathematicians alike. In classical physics, we are accustomed to perceiving the world in three spatial dimensions: length, width, and height, coupled with the dimension of time, forming the familiar four-dimensional space-time continuum. However, at the quantum level, the nature of reality becomes far more intricate, with theories suggesting the existence of additional dimensions that may interlace in ways that challenge our macroscopic understanding. This essay explores how dimensions potentially numbering far beyond the familiar four interlace at the quantum level, delving into theoretical frameworks, mathematical models, experimental evidence, and philosophical implications, defining dimensions in quantum physics. In physics, a dimension is a measurable extent of a particular kind, such as space or time. At the quantum level, dimensions take on a more abstract and complex role, often described within the context of theoretical frameworks like string theory, M-theory, and quantum gravity. These theories propose that reality may comprise more dimensions than the four we observe, with the additional dimensions being compactified or otherwise inaccessible at macroscopic scales. How many dimensions? The number of dimensions proposed in quantum theories varies depending on the framework. String theory suggests the existence of 10 dimensions, 9 spatial plus 1 temporal, in bosonic string theory, or 11 dimensions in superstring theory, which incorporates supersymmetry. M-theory unifies various string theories and posits 11 dimensions, introducing a framework where strings, membranes, and other extended objects coexist. Kaluza-Klein theory proposes an additional fifth dimension to unify gravity and electromagnetism, with the extra dimension compactified at a scale too small to observe directly. Loop quantum gravity. While not explicitly requiring extra dimensions, it reinterprets space-time at the quantum level, potentially allowing for emergent dimensional structures. Holographic principle suggests that a higher dimensional universe can be encoded on a lower dimensional boundary, such as in the ADS-CFT correspondence, which relates a five-dimensional anti-de Sitter ADS space to a four-dimensional conformal field theory, CFT. These theories collectively suggest that the universe may comprise anywhere from 5 to 11 dimensions, or possibly more, depending on the model. The interlacing of these dimensions at the quantum level is a key focus of modern theoretical physics, as it may hold the key to unifying quantum mechanics and general relativity. The mechanism of dimensional interlacing. At the quantum level, dimensions are not necessarily separate entities but can interlace, interact, or manifest in ways that affect physical phenomena. The term interlacing here refers to the complex interplay of dimensions, whether through compactification, vibrational modes, or quantum entanglement, that gives rise to the observable universe. Compactification of extra dimensions. In string theory, the additional dimensions beyond the familiar four are hypothesized to be compactified, curled up into incredibly small scales on the order of the Planck length, approximately 1.616 times 10 circumflex minus 35 meters. These compactified dimensions are often modeled as Calabi-Yau manifolds, complex geometric structures with specific topological properties that allow strings to vibrate in ways that produce the particles and forces we observe. For example, a six-dimensional Calabi-Yau manifold may be used to compactify the extra dimensions in superstring theory. The shape and size of this manifold determine the properties of particles, such as their masses and charges. The interlacing occurs because the vibrational modes of strings in these compactified dimensions influence the physics in the observable four-dimensional spacetime. For instance, the way a string vibrates in a compactified dimension might determine whether a particle appears as an electron or a quark. Quantum entanglement and dimensional connectivity. Quantum entanglement, a phenomenon where particles become correlated in ways that transcend classical notions of space and time, may also provide a mechanism for dimensional interlacing. In the context of the holographic principle, entanglement in a lower dimensional boundary can encode information about a higher dimensional bulk. For example, in the ADS-CFT correspondence, quantum entanglement in a four-dimensional conformal field theory can describe gravitational phenomena in a five-dimensional anti-de Sitter space. This suggests that dimensions are not isolated but are interconnected through quantum correlations. Entanglement entropy, a measure of the degree of entanglement, has been used to study how information in one dimension can influence another, effectively interlacing the dimensions at the quantum level. Example: black hole information paradox. The black hole information paradox provides a practical example of how dimensions may interlace. According to the holographic principle, the information content of a black hole is encoded on its two-dimensional event horizon, yet this information describes a three-dimensional interior. This suggests that quantum processes at the boundary of a black hole interlace with the higher dimensional physics inside, potentially involving additional compactified dimensions. Mathematical frameworks for dimensional interlacing. To understand how dimensions interlace, physicists rely on mathematical models that describe the geometry and dynamics of higher dimensional spaces. Below are key mathematical concepts that underpin this phenomenon. 1. String theory and vibrational modes. In string theory, particles are modeled as one-dimensional strings vibrating at different frequencies. Box phi equals sign frac 1 esquirt jar partial mu esquirt g gar mut nu partial nu phi equals sign 0, where e phi represents the string field, g emut nu is the metric tensor of the higher dimensional spacetime, and box is the D'Alembertian operator. The solutions to this equation depend on the geometry of the extra dimensions, which dictates how strings vibrate and, consequently, how dimensions interlace to produce observable particles. 2. Calabi-Yau manifolds. The geometry of compactified dimensions is often described using Calabi-Yau manifolds, which are characterized by their Ricci flat metrics and complex structure. The number of holes in these manifolds, known as Betti numbers, determines the number of possible vibrational modes, which in turn affects the particle spectrum. For example, the Hodge numbers of a Calabi-Yau manifold, such as H circumflex 1, 1 and H circumflex and 2, 1, dictate the number of massless fields in the four-dimensional theory, illustrating how the extra dimensions interlace with the observable ones. 3. Holographic principle and ADS-CFT. The ADS-CFT correspondence provides a mathematical framework for dimensional interlacing. The partition function of a conformal field theory in d dimensions is equated to the gravitational path integral in d plus 1 dimensions, z-CFT equals sign zint e s gravity, mathcal dg. This equivalence suggests that quantum interactions in a lower dimensional theory can fully describe the dynamics of a higher dimensional spacetime, providing a concrete example of dimensional interlacing. Experimental evidence and challenges. While the theoretical frameworks for extra dimensions and their interlacing are robust, direct experimental evidence remains elusive due to the minuscule scales involved. However, several experimental approaches aim to probe these ideas. 1. Large Hadron Collider, LHC. The LHC at CERN searches for signs of extra dimensions by looking for deviations in particle interactions that could indicate the presence of compactified dimensions. For instance, the production of Kaluza-Klein gravitons, hypothetical particles associated with extra dimensions, could manifest as missing energy in collision events. As of 2025, no definitive evidence has been found, but constraints on the size of extra dimensions have been tightened to scales below 10 circumflex, -18 meters. 2. Cosmological observations. Observations of the cosmic microwave background, CMB, and large-scale structure provide indirect tests of extra dimensions. For example, deviations in the gravitational constant or anomalies in the CMB power spectrum could suggest the influence of compactified dimensions. The Planck satellite data has been used to set limits on such effects, but no conclusive evidence has emerged. 3. Quantum gravity experiments. Emerging experiments in quantum gravity, such as those using quantum entanglement measurements or gravitational wave detectors like LIGO, aim to probe the quantum nature of spacetime. These experiments may indirectly reveal how dimensions interlace by detecting anomalies in space-time fluctuations. Challenges. Philosophical implications. The interlacing of dimensions at the quantum level raises profound philosophical questions about the nature of reality. Ontological status of dimensions. Are extra dimensions real in the same sense as the observable four, or are they mathematical constructs? The holographic principle suggests that higher dimensional realities may be projections of lower dimensional systems, challenging our notions of physical existence. Perception and reality. If extra dimensions interlace to produce the observable universe, why do we perceive only 4 dimensions? This may reflect limitations in human cognition or the evolutionary adaptation to macroscopic scales. Unification of physics. The interlacing of dimensions offers hope for a unified theory of quantum mechanics and gravity, potentially resolving long-standing paradoxes like the black hole information paradox. Conclusion. The interlacing of dimensions at the quantum level represents one of the most profound and speculative frontiers in modern physics. Theories like string theory, M-theory, and the holographic principle propose that the universe may comprise 5 to 11 dimensions, with extra dimensions compactified or encoded in ways that influence observable physics. Through mechanisms like compactification, quantum entanglement, and holographic duality, these dimensions interlace to produce the particles, forces, and space-time we experience. While experimental evidence remains indirect, ongoing research at facilities like the LHC and through cosmological observations continues to probe these ideas. Philosophically, the concept challenges our understanding of reality, suggesting a universe far richer and more complex than our senses can perceive. As theoretical and experimental advances continue, the interlacing of dimensions at the quantum level may unlock the secrets of the cosmos, offering a glimpse into the fundamental nature of existence.